In this video, we are going to talk about polyprotic acids, indicators, pH indicators, and which factors affect the strength of an acid. So polyprotic acids are acids that have more than one hydrogen that can ionize. So in this example, you see carbonic acid. There are two hydrogen at the beginning of the molecule. So this is telling us that there are two hydrogen in the molecule that could be released. For the first dissociation, the equilibrium constant is in the order of the 10 to the minus 7. For the second one is in the order of 10 to the minus 11. So the second dissociation, it's much harder, right? So the hydrogen are released in a sequence. The detachment of the first hydrogen is easier because it's coming out from a molecule that's neutral. But once the molecule is already negatively charged, like HCO3, then what happens is that trying to take away a second hydrogen is going to be much harder. So the second ionization constant tends always to be smaller. Now, as a reminder, if we pair these two ions with sodium, we would have sodium HCO3, and that would be sodium bicarbonate, that's also called baking soda. If we pair sodium to the other ion, we would have NH2SCO3, that would be sodium carbonate, and that would be washing soda. Now, washing soda is more basic than baking soda, and the reason is that this ion here, that's in the baking soda, that's in the washing soda, it's the conjugated base of a weaker acid, therefore it's stronger than this one. That's the one that you find in the baking soda. That's the conjugated base of a relatively stronger acid. So here you can see a sequence, three acids. You see carbonic acid once again, sulfurous acid, that's H2SO3, and again the first dissociation, the first equilibrium constant for the dissociation, so the first Ka, is much bigger than the second one. In this case, there is a factor of 1,000,000 times, right? Because one is 10 to the minus 8, the other one is 10 to the minus 2. This is sulfuric acid, so it's also a diprotic acid, this one. And so the difference is that sulfuric formula is H2SO4, sulfurous is H2SO3. For sulfuric acid, that we have classified among the strong acids, that's true for the first dissociation. For the first dissociation, the Ka is so large that we don't even have a number for it. That's the leveling effect of water as a solvent, right? So we consider it a strong acid. But the second dissociation, actually, for the second dissociation, we can in fact brought an equilibrium, and the Ka is in the order of the 10 to the minus 2. So it's for being a weak acid, it's kind of a high value, but it's still a weak acid for the second dissociation. So the reason why the first Ka is much larger typically than the second is that it's harder to remove a H plus ion from an anion that's already negatively charged, and you're trying to make it more negative. Typically, consequently, because of the huge difference, numerical difference between the two constants, only the first one is important to calculate the pH. So if you have a diprotic acid and they ask you to do the calculation for the pH, basically you need to pretend that it's a monoprotic and just focus the math on the first dissociation. Okay, so let's see the example of H2S. It's a diprotic acid. It's hydrogen sulfate. It's the one that in the lab, if you had any experience with it, was smelling of rotten eggs. So for the first dissociation, you form the bisulfide, hydrogen sulfide, and then for the second dissociation you form the iron sulfide. So the idea is that because the Ka1 is so much bigger, it's a factor of 6, so it's 1,000,000 times bigger than the Ka2, the amount of H3O plus that you will have as a result of these two equilibria, it's mostly 99% determined by this quantity. This is just a drop in the ocean of the H3O plus, right? So if I would have to consider how these two equilibrium interplay because they have a common species among them, it would be extremely complicated, right? So I need to do several simplifications. One simplification is this number in yellow is so much smaller than the one in green that its contribution is negligible. It's like putting a feather on top of an elephant. The mass is not going to be significantly different. So basically, if we are asked to calculate the pH of a solution of sulfuric acid, we can use the same approach we used for monoprotic acid. So we use an AC table. We can do the approximation that at equilibrium the concentration of H2S is pretty much the same as it was at the beginning, and then we calculate the pH, kind of ignoring completely that there is a second dissociation. If instead you're asked to calculate the concentration of the sulfide ion, okay, again, it would be really complicated to do things properly and consider all the interplay of those equilibria. So we can do another simplification. If we have assumed that the concentration of the H3O plus is mostly determined by the first dissociation and the second one is just negligible, that means that this number and this number are pretty much identical. So the concentration of the H3O plus should be higher than the concentration of the HS minus because it's coming from two sources. It's coming from the first dissociation, but it's also coming from the second one. So in theory, it should be a little bit higher than the HS minus. However, that difference is going to be extremely small because of the second constant being such a small number. So we can pretend that that's not happening. And we can pretend then these two concentrations are identical, this one and this one. If that's the case, they should be identical here as well, so I should be able to do this simplification. I'm losing my pencil, so just give me a sec here. Okay, so this, that is, should be equal to that, because if they are identical in this equation, they should be identical in this equation because it's the same formula. So if I simplify that, then the concentration of the S2 minus becomes identical to the value of the Ka for the second dissociation, right? So because of the simplicity of this is a favorite thing to ask in exam setting because supposedly, because there's pretty much no math, it is going to be really easy. Although it can be very confusing actually. So let's see an example of a setting. We have a saturated aqueous solution of a hydrogen sulfide. So it means that the hydrogen sulfide, that would be this, is as high as you could possibly have, and it also appears here. So it's saturated for that. And it's going to be 0.1 molar. So really the fact that they are telling you it's saturated, sure, it's an extra information, but it's not like you have, it doesn't have any consequence. What matters is that they're telling you what the number is. What is the pH of the solution and what is the concentration of all the other species. So for the pH, we pretend that the second dissociation doesn't even happen. Okay, so we focus only on the first one. And what we are going to do, we want to calculate the pH, so we need to know the concentration of the H3O plus, so we need to solve for this. This is going to be equal to that one. It's a little bit less because of this, but we pretending this is ridiculously small. So let's pretend that these two are identical. Then on top I have x squared, and at the bottom I should have the concentration of the H2S, so 0 or 10, minus X. But we can simplify, and because we know that the constant is very small, we can just assume that 0, 1 minus X is almost as, so we can do this simplification. 0, 1 molar minus X, pretty much identical to 0.1 molar. This way we can just plug those numbers in the equation, as you can see here, and to calculate X we don't have to use a quadratic, we just do the square root. Okay, let's imagine we are in the final where we have a certain constraint of time, so that would save us a lot of time. This is going to give us the concentration of the H3O+, so we have figured out the concentration of the H3O+, based on which we can calculate the pH doing minus log. That's also going to be the concentration of this. And then what the concentration of the H2S is given. So the other thing that's assuming, I mean, we can do the math, right? So now that we know X, 0, 1 minus 1 10 to the minus 4, if we would have to use properly the sig fig, we would have to keep only the second decimal, so we round it up to 0, 1 molar. So that shows you that our approximation was totally legit. The last thing we need to calculate is the concentration of the sulfide. So that's super easy. It's identical to this. So there is really no math that needs to be done. And this is because this and this are supposed to have the same concentration, as you can see from here. So by simplifying that, these two numbers are identical, right? So the reasoning of the people who write the tests is, well, if I ask them to calculate the concentration of the S minus, and it's a multiple choice, one of the 4 answers correspond to the Ka2, all they have to do is check that answer. There is no math, therefore it's a quick question to answer, therefore it's suitable for a final exam. Well, it's a quick question to answer if you know what you're looking for, otherwise it's quite confusing. How does a titration of a diprotic acid looks like? Now, this is carbonic acid, but you could have, you would see the same graph for example, oxalic acid, and you did perform that titration in the lab using phenolphthalein as an indicator. So, in which case you were totally oblivious of the pH, you didn't even know what the pH was, you were just waiting for the phenolphthalein to turn pink, and that would have happened here around a pH of about 10, because the oxalate is the conjugated base of a weak acid, and so therefore the pH at the end of the titration is basic. However, the titration happens in 2 steps. First, you have a complementary reaction with the first of the 2 hydrogen, and only when that reaction is completed, you have the second titration, titrating the second H+. However, because the phenolphthalein changes of color only at a relatively basic pH, you would have been totally unaware of the first half of the titration. If you would be recording the pH, though, you would see the whole progression of the thing, right? So you would see you start from an acidic pH, you have your buffer zone, and then you have the first steep rise in the pH, and where here you would have the first equivalence point. Then you would have a second, it's almost like pasting 2 titration one on top of the other. So the way to, if they give you a blank graph and they ask you what type of acid is that, you need to count the rays. It's like a stairway, you need to count the raises in the stairway. So 1 and 2, don't count the horizontal steps, count the vertical raises. Each of them correspond to 1 hydrogen. So there are 2 raises. This is a diprotic acid. If you want to see the first equivalence point, you need to use a different indicator, an indicator that changes the color around the first equivalence point pH, that is not 10, is 8. It's still basic, because bicarbonate is also the conjugated base of a weak acid. But between carbonic and carbonate is the conjugated base of bicarbonate. But between carbonic acid and bicarbonate, carbonic acid is the strongest, therefore this is quite weak. This is the strongest, therefore this is a bit stronger than that, if it makes sense. Okay, what if you have a triprotic acid, right? So again, the way that you use to determine how many hydrogen, acidic hydrogen there are in the molecule is to count the rise in the titration curve. So 1, 2, 3. So basically you're counting the midpoints. Now there are many examples. In organic acid, pretty much is only phosphoric acid. One that they use a lot for as an organic example is citric acid. That's the acid in the lemon juice. There's really not much about this. The only type of question that I can see could happen is, you know, a blank graph and figuring out that this is a triprotic acid. So what are these pH indicators like phenolphthalein? Those are substances typically with a relatively complex formula, and they need to be well soluble in water, and they are weak acids, typically organic molecules, as I say, quite complicated. So because they're weak, they have their own dissociation that is represented in this line. And the trick is that the critical thing is that the color of the undissociated form, so the one with the hydrogen, so the weak acid, has a different color from the salt, so the dissociated form. So in this case, when the indicator has still is hydrogen attached, it is yellow, and when it's in the form of a salt, it's red. Right. So from the perspective of your eyes, what's going to happen is that if you have equal amount of both forms of the indicator, so if the ratio of the HIN and IN minus is pretty much 50-50, you would see an intermediate color between red and yellow that would be orange. If you have a prevalence of the EN minus, you would see red. And if you have a prevalence of the HIN, you would see yellow. Now, what do we mean for prevalence? So most of the time, I mean, it depends on, you know, personal acuity of the visual system, training, and other things. But in general, our ability to see, when we have a mixture of two pigments, our ability to see them both depends on the relative ratio. So if one of the two is 10 times more concentrated than the other, we tend to see only one color. So if the amount of the red form of the indicator is more than 10 times the amount of the yellow form of the indicator, we would just see red. As you can imagine, if you have a titration, seeing a change of color from, let's say, yellow to red is relatively hard because you transition slowly between several shades of orange, and so it's hard for you to tell when the orange has become reddish enough to tell you that the change of color is complete. That's why in the lab we have been using phenolphthalein, because in that case it's like from colorless to pink. It's much easier to detect. For other kind of indicator, you need a little bit of training. Okay, so if the limit of our visual system is the ratio of the two different forms being 10 to 1 or 1 to 10, that corresponds to pretty much 2 units of pH based on the, you can do that with the Anderson-Hasselbalch equation, right? Because if you have weak acid and its conjugated base and they are pretty much close to a 1-to-1 ratio, you can use the Anderson-Hasselbalch equation. If the two concentrations are identical, you get the logarithm of 1, that is 0. So you get that the pH, when you have 50% of the yellow and 50% of the red, the pH is going to be equal to the pKa of the indicator. So if phenol red is 8.6, the pKa, just a reminder, the pKa is minus the logarithm of the Ka. if the pH happens to be 8.6, you would have 50% of the red form of the indicator and 50% of the yellow form of the indicator, and you would see orange. If you would have 10 times more red, then you would have a ratio, or 10 times more yellow. The ratio would become equal to 10 or equal to 0.1. The logarithm would be either 1 or -1, so you would be in a range around +1, -1 respect to the pKa. So phenolphthalein is actually has been used as a medication. It's a bit obsolete now. It was used as a laxative for small children, and you see the molecule is quite complicated. And just by losing one electron, you have a kind of a rearrangement of where the double bonds are in the molecule that changes the way it interacts with the light. And so you go from colorless, colorless is for any pH that's acid or slightly basic, so it needs to be, the pH needs to be at least 8.2 for you to see the pink. Now, different indicators would have different change in color at different pHs, right? So let's take, for example, methyl red. Methyl red is a change in color from yellow at more basic pHs, and it becomes red at more acidic pHs. Now, it's going to be useful, methyl red is going to be useful when you have a pH of about, let me get the pointer, somewhere halfway here, so let's say about 5.5, because if between, let's say, 4.5 and 6.5 you have different shades of orange. So you would know, if you see the methyl red, you add methyl red to a solution and you see that it's going to turn orange, you know that your pH is somewhere between 4.4 and 4.5 and 6.5. However, if methyl red is going to be yellow, that's not telling you much really, because it would be yellow for any pH above 6.5. So it could be 7, it would be yellow, 9, it would be yellow, 11, it would be yellow, 14, it would be yellow. So seeing yellow doesn't really tell you that much. Same if you see red, because it could be any pH below 4.5-ish, right? So it could be 1, it could be 2, it could be 3, it could be 0, you wouldn't know. Sometimes you have indicators that may have two different colors, so two subsequent changes of color. So thymol blue changes from red to yellow around a pH of 2. Then it stays yellow for a large amount of pH range, and then when you reach 7, it turns blue. Normally they don't write the color, for the whole range. They just write the color. You just get a drawing for the area where the color change happens. So, but that doesn't mean that there is a discontinuity here. In between here, it would just be constantly yellow. I guess is a way to save toner if you're printing this. But as you can see, by combining all the indicators, you can cover the whole range. So although each indicator on itself is kind of only giving you information for a limited range of pH, if you combine them all together, you can have a whole rainbow describing many different pHs. It is what we call a universal indicator, as we will see afterwards. Another indicator that you've been using in the lab was the litmus paper. Litmus paper is an indicator that has been known to since the Middle Ages. It's actually part of, let's say, normal language in English. To say that something is a litmus paper of a situation means that it is able to tell you what's going on. It's a vegetable substance of vegetable origin, is obtained by lichens, and is then either absorbed onto paper, or you can make solution out of it. And typically you have two types of litmus paper. One is pink and one is blue. And so if you have a base, the pink one will turn blue, and if you have an acid, the blue will turn pink. And that's a bit confusing because phenolphthalein turns pink in a basic solution, but litmus paper turns pink in an acidic solution. So the litmus paper doesn't really tell you a specific pH, it just tells you in general if something is acidic or basic. If you want an indicator that's more specific, you need to combine several substances that are pH indicator and mix them all together and solve them on paper. And so you get a paper that's called universal indicator. So normally at rest, let's say when dry, the paper would be typically of a greenish, yellowish color. And then when you touch the paper with a drop of the solution, you would see a color from which you can infer the pH. And normally there is a color scale on top of the box to read it. Many substances can be used to make indicators. Most many substances that are originated from plants have the ability to change color depending on the pH. Think about the hydrangea flowers that are very common in our gardens, and the flowers would be blue in a basic environment and pink in an acidic environment. So you can somehow influence the color of the flower by correcting the pH of the soil. One indicator that's really easy to make is the cabbage indicator. So you can get red cabbage and make a soak it with water, and then put it in the food processor and then filter it to separate the solid. And it can be preserved a little bit longer if you add a bit of alcohol, and it displays this really neat range of colors depending on the pH. The pH would be that little number on the top of each test tube. So why are certain substances strong acid and some others are weak acid? Now you might have noticed a trend. The larger is the number of oxygen, and the number is the number of molecule of atom of oxygen in the formula, the more acidic is the acid. So for oxyacids, for example, sulfuric H2SO4, it's a stronger acid than sulfurous H2SO3. That works also for nitric. Nitric HNO3 is a stronger acid than nitrous HNO2, especially with the hydrochloric. For the oxyacid contain chlorine. You can see that the strongest is HClO4 perchloric. And that's a strong acid. Then you have HClO3. If you remember, that's chloric, and that's the one that some books would consider strong, some books would not. It's kind of borderline because the Ka is equal to 1. So it's like dissociated 50% to some extent. And then you have the chloros, that HClO2, that's weak. And then the weakest is the HClO, hypochlorous. So you see that the less oxygen, the weaker is the acid. Now these are, by losing the hydrogen during the, those are all, in this case are monoprotic. The example in the picture with the molecular model, that's sulfurous, that's diprotic. So you're forming anions in which you have resonance forms, because in this form you have the double bond here on top, the double bond could be here, the double bond could be here. So basically what resonance forms, the potential for resonance forms, that would be 3 in this case, and it would be 4 in this case, allows the dispersion of the negative charge. So having 4 oxygen, among which disperse the 2 negative charges, as opposed to, here one got low, oh no, it's here, and as opposed to just 3 atoms, makes the molecule more stable. So the larger number of oxygen provide more room for the dispersion of the negative charges, making the anion more stable. That means it's easier to pull away the hydrogens. Another important factor, well, and here you see the hydroxy acid from like hypochlorous, chloros, chloric, and perchloric that I was mentioning before. Another important factor is what's connected to the oxygen. So you have the hydrogen that's going to be dissociating, you have the oxygen, so this is a very polar bond and the hydrogen can be detached, but it's important what's next to the oxygen. So in this case you have so in this case you have the same amount of oxygen. What's changing is the halogen. So between these three, chlorine is the most electronegative because it's at the top of its group, and iodine is the less electronegative. So because chlorine is the most electronegative, is helping sharing those. So the moment you lose the hydrogen and you acquire, so if you the hydrogen goes away, these two electrons are staying with the oxygen becomes negatively charged. The fact that there is a strongly electronegative atom nearby helps stabilizing those that negative charge. They are somehow drawn partially towards chlorine, as opposed to the oxygen as to having to carry the whole burden. The burden is shared with the chlorine. So if you look at the formula of acetic acid in sort of a Lewis structure, so this particular drawing doesn't indicate the lone pairs that would be around the oxygen. But what this picture is trying to show you is that there are different types of hydrogen in this molecule. One of the hydrogen, the one that's bonded to the oxygen, is part of a very polar bond. So because the bond between oxygen and hydrogen is so polarized, the electrons are already closer to oxygen. This is a bond that's easy to break, and when it breaks, the electrons are staying with the oxygen. So therefore the oxygen will end up being positive, and you would have the H plus that's responsible for the acidity. These other hydrogen here are bonded to carbon. That bond, carbon-hydrogen, is very lightly polar and basically is considered non-polar. There is a minimal difference of electronegativity, but it's not affecting. So those hydrogen are not acidic at all. So if you consider phosphoric acid and phosphorus acid, you would look at the formula and think that they're both triprotic, right? Because when we write the formula of acetic acid, they write that hydrogen that's different at the beginning, and the other three are left at the end of the molecule. But this happens because in organic chemistry there is more freedom, more latitude in how you can write the formula. That is why the formula of acetic acid sometimes is written in quite different ways. In inorganic, so when you're writing the formula of phosphoric acid or sulfuric acid or NaOH and so forth, the order is a bit restricted by order of electronegativity. So what happens is that you write these two the same way, with free hydrogen at the beginning of the molecule, even if the structure between the structure of these two molecules is quite different. So in phosphoric acid, all three of those hydrogen are bonded to oxygen. So they are all polar, those bonds are polar enough to make all three hydrogen acidic. So phosphoric acid is a triprotic acid. Phosphorus acid is not, is only diprotic. One of the hydrogen is different, and is this one. This one is bonded directly to the phosphorus. The bond is not polar enough to make this hydrogen acidic, right? So because of this peculiarity, this can be kind of a sneaky question that could come up in a test. Not, I wouldn't put that, but I don't know what's going to happen with the final. That's what I'm saying. So let's consider the reaction of hydrochloric acid and sodium hydroxide. That's an irreversible reaction that goes only one way, and that's really good because if you think about it, it would be really awful whenever you put kitchen salt, table salt in the water, if you would be producing hydrochloric acid, that's muriatic acid, and sodium hydroxide, and that's the stuff that you put in the drain when it's clogged, right? That would be really terrible. Instead of, you know, having salt water to boil your pasta, you would poison yourself, you would kill yourself. So that's an example of a reaction that goes only one way. However, this is because hydrochloric acid is a strong acid and sodium hydroxide is a strong base. So the salt that we obtain is neutral and does not interact with the water, giving back is the acid and the salt. But that's not always the case. Sometimes the component of the salt, the anion and the cation, may react with the water producing small amounts of their parent acids and bases. And that's a process that is the reverse of an acid-base reaction, of a neutralization. This process is called salt hydrolysis. So let's see some example. In this first example, we have sodium chloride. So in order to figure out which are the parents acid and base for this salt, we're going to divide the salt into the two ions, the cation and the anion. So we have sodium ion and chloride ion, and then we are going to add an OH minus to the cation, and we get an hydroxide, and we are going to add an H plus to the chloride, and so we get hydrochloric acid, so we get an acid. So here are the parents, acid and base of this salt. Then we need to classify them as strong or weak. So sodium hydroxide is a strong base. This tells us that its conjugated acid is going to be weak. Hydrochloric acid is a strong acid, and this tells us that its conjugated base is also going to be weak. So because everything is weak, the salt is neutral and will not interact with water. Let's consider ammonium chloride. When we divide it, we get ammonium ions, and those correspond to ammonium hydroxide. That's basically the formula that we use when ammonia is dissolved in water. That's a weak base. That means that its conjugated acid is strong, and this will make the salt acidic. So when we put an ammonium salt, like for example ammonium chloride, in water, it will react with the water. That would be the hydrolysis reaction, forming a small amount of ammonia and H3O+. So this will make the solution acidic. The other example is sodium fluoride. So we divide it into halves. We get a strong base, sodium hydroxide, but we get a weak acid, hydrofluoric acid. So the conjugated base of this weak acid, fluorine, is a strong base, and this will make the salt basic. So if we put a fluoride in water, it will react with the water, forming HF and forming OH-, and therefore the solution is going to be basic. So this is a recap of the possible combination. Of course, there is a fourth combination that I didn't consider, that is weak acid and weak base, in which case both the anion and the cation will have an hydrolysis, and so the total effect depends on, sure, because weak is just a generic classification, but which one is the weakest, right? So the hydrolysis of the salt will depend from the relative strength. And so you would have to do some math about it. You would need to know the acidity constant of the two weak acid and so forth. Therefore, the example that you get in test tends to be only referring to this combination, because for this one you don't need any math.